Hi guys, for our first flipped lesson we're doing section 2.1, which deals with representing relations and functions. There's a lot of vocab and it's quite a long section, so I'll get right started. First of all, some review here. A relation is a mapping or pairing of input values with output values. Usually we call the input values domain or X and the output values range or Y. So a relation is not a function necessarily. All functions are relations, but not all relations are functions. So there's some examples here of relations, and basically any ordered pairs, any group of ordered pairs is a relation, but they're not all functions. And like it says here, domain, usually we call that X, range, usually we call that Y. So these would be the domain values right here, what normally is the first number in an ordered pair, and we call that X, and the second set of numbers in the ordered pair, we call that Y. So usually we refer to this as domain and this is range. And it can be represented in various forms. You're familiar with ordered pairs, tables, graphs, and mapping diagrams. So let's go ahead and answer an example here. So example 1 says, consider this relation given by these ordered pairs. It says identify the domain and range. So again, domain usually means X values, range Y values. So these are all our X's. You all know that. So our domain, now the thing you have to be careful of, domain, if there's repeating numbers, you don't write them down twice. So in our example here, it doesn't look like we have repeating domain numbers, so we can just list them all. So it would be, domain would be -2, -1, 1, 2, and 3. And for range, we're looking at the second number in the ordered pair, which is usually what we call Y. And so for range, we list the numbers 2, try not to repeat any numbers. You can see here we have 1 that's repeated twice. So you don't have to write it twice, you just write it once. And we try and keep the numbers in the right order as they would be on a number line from small to big. So -3, we've got -2 over here. We've got 1 that repeats. And we've got 3. So that's a domain and range for this set of ordered pairs. And then the second part asks us to represent a relation using a graph and a mapping diagram. So here's the graph. Obviously we'll do that in a mapping diagram. So let me go ahead and clear that, and I'll make the mapping diagram over here as well. So mapping diagram usually looks something like this, with input output, and based on your domain and range you can just fill this in. Let's go ahead and call this input, call this output, and so we have -2, -1, 1, 2, and 3, and then output -3, -2, 1, and 3. And so you just follow this set of ordered pairs to create the mapping. So -2 goes to -3, so you just draw an arrow showing the relationship. -1 goes to 1, 1 goes to 3, 2 goes to -2, and 3 maps to 1. And so you get a crisscross mixed up bunch of arrows here, but that is a mapping diagram that illustrates that relation. And then if you want to graph them, again, we're just plotting ordered pairs. So -2, -3 down here, -1, 1, 1, 3, 2, -2, and 3, 1. And please remember that this is just a relation. Did I miss something? Nope, doesn't look like it. So this is just a relation, and you don't have to connect the dots. You're just drawing the dots. You're just plotting the points. You're not connecting them. All right, so let's move on. Let's try another one exactly like it. I'll go a bit faster this time. Another relation, bunch of ordered pairs, identify domain and range. So domain again are the x values. So in this case, our domain, if you avoid the repeating numbers, is -4, -2, 0, and 1. You can see here that -2 repeats, okay? And then range, our y values is are -4, -2, 1, and 3. Again, 3 repeats, and I try to keep them in order from least to greatest. All right, so that's the domain and range. And then this time they're asking us to represent the relation using a table and a mapping diagram. So tables are nothing new to you. Kind of hard to draw a table nicely here with my tablet, but tables are nothing new to you. We've been doing these forever. So I'll try and speed this up a little bit. You're basically just writing in the ordered pairs, okay? So -4, 3, -2, 1, 0, 3, 1, -2, and -2, -4. So that's the table, and the mapping diagram, just like we did earlier, you're just drawing arrows to show how things match up. You've got an input, you've got an output, okay, and this is a bit easier because we have repeating numbers, so we're actually not going to use all these values. We're just going to write down the numbers once. So we have that for the domain, this for the range, okay, and we're just going to show how they map. So for the mapping, you go here, -4 goes to 3, -2 goes to 1, 0 goes to 3, 1 goes to -2, and -2 goes to -4. Okay, so you've got some overlapping, crisscrossing stuff there, but that's the mapping diagram, right? So mapping diagram, table, domain, and range. Let's keep going. So some other vocab here, a function. This is just the definition of a function. I'm sure you already know this, but it's something we have to go over again. A function is a relation for which each input has exactly one output. Each input has exactly one output. So if I put in a number, I have to get the same output every time for that number. If any input of a relation has more than one output, the relation is not a function. So you just remember this. Each input has exactly one output. Otherwise, it's not a function. Okay? More than one output, it's not a function. So I'll give you a quick little overview of what that means. Here we've got a mapping diagram of a relation. Here's the number 2. 2 is mapping to the number 3. That's fine. It has one output. But now 2 also maps to 5, and it also maps to 4. That's more than one output. So because 2 maps to 1, 2, 3 different numbers, 2 is one input number, goes to 3 different output numbers, it's not a function. Okay, it's not func. Next one, we look at this table here. So these are the inputs, these are the outputs. So 3 maps to 5, 5 maps to 5, 8 maps to 1, 1 maps to 8, 3 maps to 5, and 6 maps to 8. Now 3 shows up twice. 3 maps to 5. Now that might look like a problem, but it's not. 3 can map to 5, that's fine, as long as every time you see 3 in the input, you see 5 for the output. That's only one output, that's fine. The output is 5. No problem. And also 5 can map to 5, even though 3 maps to 5, that's also okay, as long as 5 maps to 5 only. So this table here is a function because it meets the definition. Each input has exactly one output. So this is a function. This mapping diagram here, let's see if you can figure that one out. 15 goes one place. Basically, fairly easy. All these numbers are different numbers, and they map only to one number, one arrow each. So that's fairly simple to see that this one meets the definition of a function. Okay, and then if we look at this table, we look at 325 goes to 50, 350 goes to 50, that's fine. They're different inputs with one output each so far, that's fine. 375, happy, happy, happy. Oh, here's the problem. 325 goes to 50, 325 goes to 175. That's one input with two outputs, not one output. It's got two outputs. I put in 325, I get out 50. I put in 325, now I get 175. That's not allowed to happen for a function. So this is not a function. It is a relation, but it's not a function. Okay, it doesn't meet the definition. Let's look at some more examples real quick. So again, same question. Tell whether the relation is a function. These are mapping diagrams. That's a table. So very quickly, 3 goes to 2. Fine. 1 goes to 3. Fine. 2 goes to 4. Negative 4. Fine. 4 goes to negative 4. Fine. This is a function. No problem. Every input has one output. That's fine. No problem. This is the case where we have issues. When one input goes to two outputs. So this is the problem. 1 maps to negative 1 and 1 maps to 2. That can happen. That's one input with more than one output. So this is not a function. Okay, and then here, this might look problematic, but you see these are all different inputs, and they have the same output, but that's fine. Negative 2 maps to negative 4, negative 1 maps to negative 4. They all map to negative 4, but they don't map to two different numbers. They all map to the same number every time. So that's okay. This is fine. This is also a function. And you probably know what this looks like when you graph it, but we'll get there maybe in section 2.2. All right, so some more vocabulary here. We've been talking about looking at numbers in tables and mapping diagrams and ordered pairs to determine if something is a function. There's also a way you can do that graphically, which is the vertical line test. So the vertical line test says you can use a graph of a relation to see if it's a function. And the vertical line test says basically if you look at a graph of a function and you draw a line, vertical line, anywhere on the graph, it only crosses the graph once when it's a function. If a relation is not a function, if you can draw a line, a vertical line, anywhere on the graph that is able to touch that function twice, or that relation twice, then it's not a function. So this is a function because the vertical line only touches the graph once when I draw it anywhere on the graph. This is not a function because when you draw a vertical line in many places on this graph, it'll cross the relation twice. So that makes this not a function. It's a relation but not a function. Okay? So that's the vertical line test that you've probably done in Algebra 1. So let's go and actually apply that to some graphs and see what we get. So this one, vertical line test. Can I draw a vertical line anywhere that will cross the graph twice? And yes, the answer is yes. If I draw a vertical line here, it crosses twice. So this is a relation, but it's not a function. And now here, you can draw a vertical line in many places, but you're not going to make the vertical line cross this relation more than once. It only crosses it once. So anywhere you try and draw a line there, only crosses once. So this definitely is a function. It's not just a relation, it's a function as well. Okay, here same thing. You can draw vertical lines. It's not a very usual function, but it doesn't cross anywhere more than once. So this is also a function. And in here we have a circle. Of course, easy to see, I can draw a vertical line many places here, and it'll cross the circle twice. So this is not a function. Of course, here I didn't write not function, but this is not a function. This is not a function because the vertical line crosses the graph twice. Different kind down here in number 5 and 6. Very similar, but this is just like a little scatter plot of points, and you need to be able to recognize this as well. So if you look at this, you can still use the vertical line test. Now you can see these are all vertical lines here, and they only cross every point once. No problem there. But here we have the issue. Here's a vertical line that touches 2 points in this relation. So this would be a function, because every vertical line here only touches one piece of data or one part of the graph, but this vertical line crosses 2 pieces of the graph, 2 points, and so this is not a function. Okay, I hope that's clear. We've done quite a few examples of that now. So the vertical line test is a very quick and easy way to see from a graph if it's a function or not. Alright, so then let's talk about equations in 2 variables. So you're very familiar with these, you've graphed these, you've done all kinds of things with these. And so this should also be a fairly brief little review for you. The way that they're asking us to graph it here in section 2.1 is to graph these functions by using a table of values. So I'm going to do that in a very quick and easy way, but you probably know other ways too. Just something to note, vocabulary here. The independent variable is the input. Okay, so most of the time it's x, sometimes it's t, something like that. Independent variable is the input, usually it's x. The dependent variable is the variable that depends on the independent variable. So most of the time that's y. Most of the time we have a function that says y equals to something x plus or minus something. And so y is the dependent variable, x is the independent variable. X is the input, y is the output. Those are basically how those things work most of the time. And we know that if an ordered pair is a solution, when you plug this into the function, it works. You get something that's true. We've already been doing stuff like that, but just with 1 variable, not 2 this year. But you've done this in the past, so this is nothing new. So let's quickly get through this one. To graph this kind of equation, which you'll see a little bit later, it's called linear, you really only need to make a table of 3 values. Okay, you don't really need more than 3. Actually, you only need 2, but I'm going to make 3 just to humor the textbook publishers here. So basically, you just need x is -1, 0, and 1. Those are the easiest 3 numbers usually to pick when you make a table of values in order to be able to find the y values or the output or the range in order to graph it. Okay, so basically we have this function y equals -2x minus 1, and so you basically are doing substitution. Y equals -2, this is x times -1 minus 1, and what you get here is basically, what's that, 2 minus 1, so 1. So when x is -1, y is 1. Okay, and we can continue with this scenario the same way. Again, for x we're substituting 0 here, -1, so negative 2 times 0 is not 2. That would be 0 minus 1, which is negative 1. Okay, so when x is 0, y is negative 1, and finally y equals negative 2 times 1 minus 1. So that's negative 2 minus 1, which is negative 3. And so this means when x is 1, y is negative 3. Okay, I know you can probably do that a lot faster. You probably do it in your head. I'm just trying to be explicit and help everybody out. So if you graph these, negative 1, 1, first point, 0, negative 1, second point, and then 1, negative 3, third point. Okay, let's see if I can get a line from this here. Maybe I can make this line go through all 3 points, sort of. Okay, so yeah, there's a line. Okay, that's what it looks like. As long as you have the right 3 points, and hopefully your line touches all 3 points, that's what it looks like. Alrighty, so yeah, same thing for example 6. Same thing. They want you to make a table of values. Again, I think you know how to do that. I'll go ahead and be a bit faster about this one, since I'm assuming that you are fairly experienced at doing this. Alright, so I'll just pick negative 1, 0, 1 again. And I've already done this, so if you do all the substitutions, which I'm sure you can do, you get negative 8, negative 5, and negative 2. Okay, so that's your table of values. And if you plot these points, negative 1, negative 8, like down here somewhere. Okay, and then 0, negative 5 will put you about here. And then 1, negative 2 would put you down here. Okay, and so let's draw a line again through this. Hopefully I can get it straight through there. Yep, there it is. Okay, and so there's your line. All right, so this is an equation, and if you look at this, at least from what we can see so far, if you do a vertical line test on this, it looks like it's a function. So yeah. All right. So now let's talk about linear. So what we just graphed were 2 linear functions. Linear comes from the fact that they make a line when you graph them. Gets more complicated than that, but for our purposes, that's fine. And then also, and there's a very easy way to identify if something is linear, and that basically is if the highest power on the variable is 1. So here's an example of a linear function, okay, and the variable here is x, variable here is y. Most of the time we're talking about the x variable having the power 1. When the highest power in an equation or a function of x is 1, then we call it linear. Now that's also true for y, but we don't really deal with y to a different power for quite a while. So yeah, for now, linear for you means basically x to the first power. If there's anything higher than x to the first power, or anything different from x to the first power, it's probably not linear. Okay, there are a few exceptions to that, and we'll see that. Any case, so this is a linear function, okay, because it can be written in this form, where m and b are constants, in other words, numbers. The graph of these functions are all lines. It's a simple way to remember that. Okay. Also, the other big thing here that you need to note is function notation. We're going to deal with this more and more. Function notation means it's a little bit more descriptive, a little bit better. Instead of writing y equals negative 2x minus 1, you can write f of x, a function of x, equals negative 2x minus 1. This is a little bit more useful sometimes because it tells us what the input was to get a specific output. Okay, and you'll see that in a second. So yeah, these two things mean the same thing, except this is function notation. Okay, function notation. All right. So you know this as slope-intercept form from Algebra 1. All right. So example 7. The question is, use that information we just had there, tell whether the function is linear. Okay, is this function linear? It's a question. Is it linear? Okay, and after you've answered the question, then plug in -2 and see what you get for the answer. So we can work through this fairly quickly too. So we said usually we're looking for x to the first power. In this case, we have a square. Most of you know what this is. When you graph it, it's definitely not a line. But also because of the second power in the variable here, if you just look at the equation, you can know this is not linear. Okay, so you say it's not linear. All right, this is definitely not linear. And then substitute -2 in there. So let's evaluate the function. So f at -2, f of -2, okay, equals -2 squared minus 2x plus 7. Okay. Oops, sorry, forgive me there. Not minus 2x. We want to substitute. So minus 2 times -2 plus 7. Okay. And so I have here -2 squared is 4. This negative just comes down. And negative times negative positive, that's a 4 plus 7. So what I get here, these two go away, so my answer is 7. Okay? Simple. Simple. Plug in a value. We read this f of x equals -x squared minus 2x plus 7, so this is f of -2. Okay? Same way here, f of x equals x minus 1 minus x cubed. Is it linear? Nope, because it's the cube here, so this is not linear. Okay? And there are some tricky things people can ask you there, but this is not linear. This is a simple example. And so you do f of -2. Again, I'm taking -2 and plugging it in here for all the x's. So f of -2 is -2 minus 1 minus -2 cubed. Okay, just plug in for the x, substitution. And you get here -2 minus 1. And this is minus, comes down. -2 cubed is -8. Negative cubed is -8. Okay, and so you get -3 plus 8, which turns out to be 5. All right. I think you're okay with that, substituting values. You've been doing that already this year, and I'm sure you've done that before. So I'll go a little bit faster on these last two examples. Main thing here is, are they linear? Are these two functions linear? Yes, this is the power 1. This is power 1. They're definitely linear. If you graph these, you get a line. All the variables are power 1. It can be written in the form mx plus b. So this is all fine. This is definitely linear. They meet the definition, and so these are both linear. Okay, they're both linear. And if you go and substitute the values, you're going to get g of -2 equals 5 times -2 plus 8, and if you do that, you end up with -2. Okay, and this one, g of -2 is -4 minus 2 times -2. If you simplify that, you find the answer is 0. Okay, so function notation here as opposed to y equals. Same thing, same meaning, just a little bit more descriptive as to what happened here. If I had y in here, I wouldn't know that I substituted a -2. So it's a little bit better, a little bit clearer in describing what we did. All right, last example. It's kind of a long one, okay? And this is a bit more practical, where you have to come up and think about domain and range a little bit more. And so we'll just dive right in here and talk about this example. It involves quite a few steps. So it says a climber on Mount Rainier in Washington hikes from an elevation of 5,400 feet above sea level to Camp Muir, which has an elevation of 10,100 feet. All right. Then it says the elevation h in feet as the climber ascends can be modeled by this function. Okay? Where t is time in hours. So I'm trying to underline things that may be important. Graph the function, determine a reasonable domain and range, and then they ask you a question after that. Okay, so let's read this. So the guy's climbing from 5,400 feet to 10,100 feet. Okay? And the function is h of t equals 1,000 t plus 5,400. So in this case, let me write that down actually. H of t equals 1,000 t plus 5,400. Okay. So in this case, the independent variable is t. Okay, the input is t, which is time in hours. The thing that is independent is t, the time in hours. Okay, how much time he spends determines his height. That's basically what they're saying here. So this would be my input or my independent variable, and this would be my output. Okay. In other words, t are my domain values, and h of t or h are my range values. Okay, so when they're asking for graph the function and determine a reasonable domain and range, we said earlier domain is input, range is output. So it's important here to figure out which one's which. So they kind of already gave you the output, the range, because the height in feet, they said, goes from 5,400 to 10,100. So you already actually know that the range, the outputs, the height he's going to achieve from climbing goes from 5,400 to 10,100 feet. This is my range. We need to figure out the domain. So I have the function and I have my range. So if I take my lowest range value and I plug it in here, I can figure out my domain value. Okay, my lowest domain value. And if I take my highest range value and plug it in here for h of t, this is h of t, then I can find my highest domain value. So that's exactly what we'll do. All right, so let's answer this question first. Let's find a domain and range, a reasonable domain and range. So reasonable for this question is that the person is climbing from 5,400 to 10,100. So let's do that. Let's take the lower extreme of the range, 5,400, and substitute it in here. Okay, so I'm saying in that function 5,400 equals 1,000 t plus 5,400. Now you can see what happens here. If I subtract 5,400 both sides, this goes, now I have 0 equals 1,000 t. And so you know that means that t is 0. Okay? So time is the domain we're looking for. This is the range, we're looking for the domain. So I plugged in my lowest extreme on the domain to find my lowest extreme on the range. All right? And then I plug in my highest extreme on the range to find my highest extreme on the domain. So 10,100 equals, so I'm plugging it in here, 10,100, okay, second time, equals 1,000 t plus 5,400. Okay, and now I'm solving this. So you take away 5,400 both sides, and you get 4,700 equals 1,000 t. Divide by 1,000. All right, and so t is 4.7. So the upper extreme is 4.7. again, let's go over that real quick. We took the lower extreme, plugged it into our function, okay, and we ended up with the lower extreme for the domain, because we had the lower extreme for the range, so we found the lower extreme for the domain, which is t, okay, and then we took the upper extreme for the range, plugged in that same function again, and then we got the upper extreme for the domain. So this is domain and range. Right, we've answered some of the question. They also want you to graph. Okay, I mean, we have some data points here. This is basically a point. We can say that 0, 5400 is one data point, and this is another one. Okay, 4.7 and 10,100. That's another data point. So these are my two data points. You can make a graph with that fairly simply. Let's do some enumeration here. Okay, 1, 2, 3, 4, 5, and let's say this is time in hours. Okay, and this would be height in feet. And over here, I'm just going to do this very quickly, very simply. Let's call this 5,000, and let's call this 10,000. Okay, and so we have some points here, 0, 5,400. So obviously this is 0. So 0, 5,400, maybe we'll put you somewhere up here as a point. Let me change the color there. Okay, maybe here as a point. And then 4.7, 10,100, 4.7, 10,100, maybe around there, okay? If you want to be super accurate, you have to do all this with a ruler and all that kind of stuff. But roughly, this is what you end up with, okay? There's the graph. And then there is one more question, and it says, what is the climber's elevation after hiking for 3.5 hours? Don't need any of this work we did. You just need the function, and you're just substituting. So I'm going to take all that away. Basically what you're doing is you're saying h of t equals 1000t plus 5400, and they're saying what happens when t is 3.5. So h of 3.5 equals 1000 times 3.5 plus 5400. Okay, and you're simplifying this. So what you get is 3,500 plus 5,400, and the result is 8,900 feet. So after 3.5 hours using this function, the climber will be at 8,900 feet. Okay guys, so I hope that was helpful for you. Please make sure that you've taken down all these examples in your notebook. We'll be looking at this again when we meet next class, and we'll be doing some classwork and practice and check for understanding. Thanks, I hope you enjoyed this.